All right, in this video, we're going to talk about the probability of multiple events, not just a single event happening at one time. We're going to talk about independent events and mutually exclusive events. We're going to touch on dependent events as well, but we're going to talk more about that tomorrow. So let's go ahead and get started. Here we have independent events. An independent event is when an outcome of one event does not affect the outcome of a second event. An example of this would be the probability of flipping a coin 3 times in a row. And let's say we did that and we wanted to find the probability of getting a heads 3 times in a row. We know that the probability of getting a heads the first time is a half, because there's two different things that could happen. You can have a heads or a tails, and the probability of getting a heads would be one successful event, one heads out of the total 2 events. Well, the probability of getting a heads the second time is also a half, and the probability of getting a heads the third time is also a half. So what we want to do is figure out the probability of those 3 things happening at the same time. There's a lot of ways that we can talk about this. If I did a tree diagram of this, I could have on the first flip, I could have a heads or a tails. And then the second flip, I could have a heads or a tails, and a heads or a tails. And then the third flip could be heads or tails. And you can see there's 8 different outcomes here. I could get that by taking the denominators and multiplying them together. The 2 times the 2 times the 2. There's 8 different outcomes. And only one of those outcomes is 3 heads. Heads, heads, and heads. So the probability of all 3 of these events happening is equal to 1/8. One easy way to do that is to simply take the probability of each individual event and multiplying them together. We did this in assignment number 1 when we were talking about the different arrangements that things can be in. It also works with probabilities. And so if the probability of the first event is a half, and the probability of the second event is a half, and the probability of the third event is a half, the probability of those 3 events happening concurrently back to back to back is 1/8. Because I would multiply them together. This formula right here is something you probably want to write down and put in your notes, because the probability of 2 events happening back to back, that's the probability of A and B. Sometimes we write this as the probability of A intersected with B. That's what you can consider that kind of like an and symbol, is the probability of the first event times the probability of the second event. So dependent events are when the outcome of one event affects the outcome of the second event. An example of this would be in this situation. Let's say you want to find the probability of guessing the outcome correctly in a raffle drawing where first, second, and third place prizes are selected at random from the same pool of 10 people, and you can only win 1 prize. So for example, let's say that you want to guess who's going to win the first place prize and the second place prize and the third place prize. And so there's 10 people that are eligible for these prizes, and only 1 out of those 10 people is going to win the first place prize. Well, that person wins the first place prize, or the first place prize is chosen, and then you have the people who are left that could win the second place prize. And so there's only going to be 1, but this time it's only out of 9 people that are left, because 1 person isn't eligible anymore because that person won the first place prize. So this probability is affected by what happens here. If I go on and do the third place prize, it would only be 1 out of 8 eligible people that can win the third place prize. And the reason for that is because 2 people are now ineligible because they either won the first place prize or the second place prize. And so if I want to find the probability of all of these events happening at the same time, I would simply multiply these together, just like I did with the 1/2 times the 1/2 times the 1/2 in the last video. That's going to be 1 over 720. So the probability of guessing correctly who those 3 people might be, if it was completely random, would be 1 in 720 different outcomes. We're going to talk more about dependent events tomorrow, but know that the formula for independent events and the formula for dependent events is really the same formula. The probability of A and B is simply the probability of A times the probability of B. So let's try one of these on our own. Take a look at example number 3. If you're just watching this video for the first time, pause the video, See if you can do number 3 and then restart it, and we'll go from there. Hopefully you've done that. This is a picnic. There are 6 bags of fat-free chips and 8 bags of regular chips. There are also 10 cans of diet soda and 12 cans of regular soda. You grab a bag of chips and a can of soda without looking, and you want to find the probability that you grabbed a fat-free bag of chips and a diet soda. Well, let's first do the probability of grabbing a fat-free bag of chips. There are 6 successful bags of chips if you want it to be fat-free, out of a total of 6 plus 8 bags. That's out of 14 bags. So then, that's the probability of the first event. The probability of the second event would be the probability that you chose a diet soda, would be that there are 10 successful diet sodas out of a total of 10 plus 12, 22 sodas. So we're just going to multiply those together. One thing that we can do here is we can cross-cancel things to make it a little bit simpler. Like, for example, 10 and 14 can be reduced to 5 and 7. 6 and 22, if I reduce that, that's like 3 and 11. And so if I multiplied I don't think there's anything else that can cross-cancel here. If I multiplied the 3 times the 5, that would be 15. And the 7 times 11 would be 77. So the probability would be 15 out of 77. And if you took 15 divided by 77 on your calculator, that's about 19.4%. That's a 0.4%. Would be the probability that you pick both a fat-free bag of chips and a diet soda. Let's move on. Mutually exclusive events. Mutually exclusive event are 2 events that cannot happen at the same time. An example of this, a simple example, would be rolling a dice and getting a 2 and a 6. If you roll a dice, you can get a 2 and you can get a 6, but you can't get both a 2 and a 6. It's impossible for both of those events to happen. So these 2 events would be mutually exclusive. So what we're going to do now is, here's an example of 2 events occurring that are mutually exclusive, but it's not the probability of both of those events. It's the probability of one event happening or the other event happening. So this is a little bit different than what we just worked on in the first 3 examples. Here's the situation. Suppose a student at Homestead High School can take only 1 foreign language, and 42% of the students take Spanish, while only 16% take German. So what is the probability that a student chosen at random takes Spanish or German? Well, it's not Spanish and German, because that can't happen, because those are mutually exclusive events, and they can only take 1 foreign language. So it's the probability that they can either take Spanish or they can take German. Well, let's take a look at the first probability. We know that 42%, we could write this as a fraction, but I'm going to write it as a decimal. That's 0.42 percent, or 0.42 of the people take Spanish, and then 0.16 of the people take German. And so I'm just going to add those 2 together. 42% take Spanish, 16% take German. If I add those together, that's a total of 0.58, which is 58%. That's an 8 there. 58% of the people take either Spanish or German. That means that there's 22% that either don't take a foreign language or take maybe French or another foreign language that Homestead might offer. Probability of this event, and this is another thing that you probably should write down, if you have 2 mutually exclusive events, then the probability of A or B is simply the probability of A plus the probability of B. This is different than what we did before because of this word here. The probability of A and B happening, you'd have to multiply those 2 probabilities together. But here we're just adding those 2 things. So the probability of 2 mutually exclusive events happening, one or the other happening, is just where you add those together. Here's where it gets a little tricky. Non-mutually exclusive events. Let's take a look at this situation. What is the probability of drawing a card from a deck of cards and getting a queen or a heart? Well, we know that if I have a deck of cards, maybe you don't know this, but there are 52 cards in a deck of cards. And 1/4 of them, 13, are hearts, and 4 are queens. And so we could think of it this way. We could say the probability of drawing a queen is 4 out of 52. And the probability of drawing a heart is 13 out of 52. And if we added those together, that would be 17 out of 32. The problem with that is that one of those cards has showed up twice. There's the Queen of Hearts. The Queen of Hearts is in this probability, but it's also in this probability. In other words, we have, if I drew a Venn diagram of this, we could have all of these are queens. We know there are 4 queens altogether. 4 queens in this circle. And if this is all the hearts, we know that there are 13 hearts in this circle. But there's one that is in both circles. That's the Queen of Hearts, which means that there's going to be 3 here, and there's going to be 12 hearts that are not the queen. And if I add those together, 3 plus 1 is 4, and 4 plus the 12, that's 16 cards out of the 52. That's the probability. What we'd have to do here is this. We would have to take the probability of drawing a queen plus the probability of drawing a heart minus the probability of drawing a queen and a heart. There's one queen, or there's one card that's both a queen and a heart out of the 52 cards. This would be my formula for this. That would give me 16 out of 52. I want you to write this formula down. This is an important formula to remember when you are talking about non-mutually exclusive events. The probability of A or B happening is the probability of A plus the probability of B, but then I have to subtract the intersection of those two sets because they're counted twice, and so I have to make sure I subtract the intersection. Let's take a look at a situation here and see if you can do this on your own. Again, here I would encourage you to pause the video, see if you can do this problem on your own, and then restart the video. It says a survey of freshmen at Homestead about sports, specifically basketball and soccer, they have played growing up resulted in the following information. 24 played soccer and 29 played basketball. 13 played both and 10 people didn't play either of those sports. So we're supposed to figure out what is the probability that a student in the survey played only one of those two sports. Okay, so that would be the probability that someone either played basketball or they played soccer. That's what I'm going to try to figure out. Might help with this Venn diagram. We're going to start with the intersection. There are 13 people who played both. So there's 13 people who played soccer and basketball. We know that there are 24 people who played soccer. So that means I have to have 11 here because 11 plus the 13 adds up to a total of 24. We also know that 29 people played basketball. And if 13 are here, 16 have to be just there because the 13 plus the 16 add up to 29. And there's 10 people outside of the circle who didn't play in either sport. So what we're going to have to do is find the probability of the people who played basketball. Well, that's 29 out of 50. Plus, that's these two. Plus the probability of the people who played soccer. Well, that's 24 out of 50. And then we're going to subtract the intersection of those two sets, which is the 13 out of 50. That's going to give us the probability of people who played in only one sport. And so that's going to be a total of, I think, 27 out of 50. Maybe that's not right. Is that right? 29 plus 24, that's 43. This is 50 here, by the way. I messed up there. So I'm going to have, okay, so I asked the wrong question. What's the probability that a student in the survey played not in only one of those sports, but played either basketball or soccer? And that would be the 29 plus the 24, which is 43 minus 13. That would be the 30 out of 50 played one of the sports. And I could get that if I added all of these together. the 11 plus the 13 plus the 16 adds up to a total